Hello students, welcome to the lecture on three-dimensional geometry, and after the lecture we will be able to learn the following objectives. Understand three-dimensional space, understand the dot product, explain the quasi-quas inequality, explain triangle inequality for distance, understand Joule-Simstalde ratio formulae. Let us start with a brief introduction of three-dimensional geometry. A vector algebra approach to three-dimensional geometry is to present standard properties of lines and planes with minimum use of complicated three-dimensional diagrams such as those involving similar triangles. Points are defined as ordered triples of real numbers, and the distance between points is defined as given by the formula. Director line segments AB are introduced as three-dimensional column vectors. If A is equal to x1, y1, z1 and B is equal to x2, y2, z2, then AB vector is as given on the screen. If P is the point, we let P is equal to OP and call P the position vector of P. Equality of vectors. Suppose A, B, C, D are distinct points such that no three are collinear. Then AB vector is equal to CD vector. Addition of vectors obeys the parallelogram law. Let A, B, C be non-collinear. Then AC bar plus AC bar is equal to AD bar. Scalar multiplication of vectors. Let AP is equal to T into AB, where A and B are distinct points, then P is on the line AB. Here AP by AB is equal to mode of T. Now we will talk about three-dimensional space. Three-dimensional space is the set 3 to the power of E of ordered triples x, y, z, where x, y, z are real numbers. The triple is called a point P in 3 to the power of E, and we write P equal to open bracket x, y, z, close bracket. The numbers x, y, z are called respectively the x, y, z coordinates of P. The coordinate x's are the sets of points. See on screen, the only point common to all three x's is the origin O equal to open bracket 0, 0 and 0. The coordinate planes are the sets of points as shown on screen. The positive octant consists of the points where x greater than 0 or y greater than 0 or z greater than 0. We think of the points x, y, z with z greater than 0 as lying above the xy minus plane, and those with z less than 0 as lying beneath the xy minus plane. The distance P1, P2 between points P1, x1, y1, z1 and P2, x2, y2, z2 is defined by the formula shown on the screen. For example, if P is equal to x, y, z, then OP is equal to square root of x square plus y square plus z square.
We've talked about one and two dimensional spaces. Let's talk about three-dimensional space. Every point in a three-dimensional space can be described by a triple of numbers, x, y, and z. Now, it's not so easy to depict a three-dimensional space on a flat piece of paper or a computer screen, so we have to imply their values by drawing boxes. I'll show you what I mean. For example, let's plot the points 2, 3, 1 and negative 1, 1, 3. First we need an x-axis and a y-axis and a z-axis. Now, why did I lay them out this way? Traditionally speaking, if you point your hand in the direction of the x-axis and then curl your fingers toward the y-axis, your thumb should point in the z direction. This is called the right-hand rule. Anyway, so we want to plot the point 2, 3, and 1. That is 2 on the x-axis. So we want to be 2 on the x-axis, which means we want to have our x value. Oh, that's a bad line. No. We want our x value to be somewhere along that line. We want 3 on the y-axis. So here's 3, 1, 2, 3. So we want our y value to be somewhere there, but we also want to be 1 point up. So we want something like this, We draw over like this. We draw over like this. And we've made a box. How do I emphasize this box? We have made a box that is... We have made a box... Ugh, it's hard to see. Let's get rid of that last line, those last lines. We've made a box that is 2 wide, along parallel to the x direction, 3 wide, parallel to the y direction, and 1 up and down. So this point right here at the very tip is the point 2, 3, 1. Well, I'm going to indicate that. 2, 3, 1. Now to plot -1, 1, 3. Oh, let me clean all this up. Is there a way for me to do that faster? Not really. -1, 1, 3. We want -1 in the x direction, so we want somewhere down here. +1 in the y direction, so we go this way, and we go 1, 2, 3 up, which means we have sort of this box. 3 tall and 1 wide and -1 in the x direction. So this point up here is the point -1, 1, 3. Do I expect you to be able to do this? Oh, I guess not. But I want you to understand that you can describe any point in a three-dimensional space with 3 different coordinates. The people who design parts of and machinery and such like that, they use what's called CAD/CAM, computer-aided design, and the computers keep track of this sort of thing for them. And you can describe the shape of an object giving its 3-dimensional components. There are now 3D printers now. They can print with little bits of plastic, squirting plastic. They can create 3-dimensional objects that have never been able to be created before. But you have to specify in 3-dimensional coordinates where you want every little glob of plastic stuck together. Very, very exciting. So, anyway, this is a 3-dimensional space. There are 3 dimensions to travel in. At this point, if you want to make your x-coordinate a little bit higher, you could move in this direction. If you want to make your y-coordinate higher, you could go in this direction. If you wanted your z-coordinate to get bigger, you could move around. You have 3 degrees of freedom. So, this is 3-dimensional.
Students, let us discuss about dot product. If X is matrix of A1, B1 and C1 and Y is matrix of A2, B2 and C2, then the dot product of matrix X and Y is defined by XY equal A1, A2 plus B1, B2 plus C1, C2. Equality of vectors. Addition and subtraction of vectors. The dot product has the following properties. X dot Y plus Z is equal to X dot Y plus X dot Z. X dot Y equal to Y dot X. Tx dot Y is equal to T into X dot Y. Vectors having unit length are called unit vectors. The vectors I, J and K are unit vectors.
Alright, so one of the uses of the dot product is actually helps us to relate an angle between 2 vectors. So if we have vector A and B with an angle of theta in between them, it turns out that cosine of theta is going to equal the dot product A dot B divided by the magnitude of A times the magnitude of B. So what we're going to do is find some angles between some vectors. So in part A we've got vector 1, 2, 3, vector B is -3, -1, 4. So we'll figure out the angle by using, again, our little formula. So a couple things here. The magnitude of A, so that's going to be 1 squared plus 2 squared plus 3 squared. Let's see, that's 9 plus, so 9 and 1 is 10 plus 4. We'll get the square root of 14. The magnitude of vector B, we'll have to take -3 and square it, -1 and square it, and then we'll add 4 squared. So let's see, -3 squared is 9, -1 squared is 1, 4 squared is going to be 16. So it looks like we've got 10 plus 16, or the square root of 26. Now we also have to figure out the dot product, A dot B. So to do the dot product, recall we just multiply respective components. So we'll get 1 times negative 3, which is going to be negative 3, plus we'll do 2 times negative 1, which is going to be negative 2, plus, and then we'll multiply 3 times 4, which is going to be 12. So let's see, negative 3 plus negative 2 is negative 5. Negative 5 plus 12 is going to give us positive 7. So when we use our formula, we'll have cosine of theta. It says, again, that's A dot B over the magnitude of A times the magnitude of B. So we'll get cosine of theta equals, let's see, the dot product was equal to 7. And then we have the square root of 14 times the square root of 26. So I'm going to simplify this down a little bit. I'm definitely going to start estimating here. So let's see, 14 times 26, that's 364. So we've got the square root of 364. Well, let's see, the square root of 364 is roughly 19.08. Alright, so we're almost there. We've got cosine of theta equals 7 divided by 19.08. So that's going to give us 0.367 after rounding. And then to figure out the angle, we'll just do inverse cosine of both sides. So we'll have to do the inverse cosine of 0.367. So let's see, 0.367. I am getting arc cosine of 0.367 to be roughly equal to 68.47 degrees. So somewhere between 68 and 67 degrees, 68 and 67, how about 68 and 69 degrees? Our angle is going to be somewhere between 68 and 69 degrees. I think I was looking at that 7. So again, that's really all there is to it. Just calculating some magnitudes, calculating your dot product, using inverse cosine, and that's about it.
Every vector is a linear combination of I, j and k. Now we will understand what lines are. A line in E to the power 3 is a set L of P subscript O, X consisting of all points P satisfying P equal to P subscript O plus Tx, wherein T is element of R, or equivalently P subscript P equal to Tx for some fixed point P subscript O and fixed non-zero vector X. In terms of coordinates, the above equation becomes as shown on the screen. Theorem 1. If A and B are distinct points, there is one and only one line containing A and B, namely L, A negative, AB, or more explicitly, the line defined by AP vector is equal to T into AB vector, or equivalently, in terms of position vectors, look at the screen. Above equation may be expressed in terms of coordinates. If A is equal to x1, y1, z1 and b is equal to x2, y2, z2, then we have x, y and z as shown on the screen. There is an important geometric significance in the number t of the above equation of the line through A and B. Theorem 2. Joule-Simstal's ratio formulae. If t is the parameter occurring in the theorem 1, then let us clarify the angle between two vectors. Let x and y be non-zero vectors, then the angle between x and y is a unique value of theta defined by cos theta equal to x into y divided by absolute x into absolute y. Here theta is greater than 0 and less than equal to pi. By Cauchy's inequality, minus 1 less than or equal to x into y divided by absolute x into absolute y less than or equal to 1. So the above equation does define an angle theta. In terms of components, if x equal to a1, b1 and c1, superscript t, and y equal to a2, b2 and c2, superscript t, then cos theta is equal to as shown on the screen. The next result is the well-known cosine rule for a triangle. Theorem 1. Cosine rule. If A, B, C are points with A is not equal to B and A is not equal to C, then the angle phi between vectors AB and AC, then cos theta value is as shown on the screen. Similar value of cos theta value is as shown on the screen. Hence you can see the proof of this theorem. Theorem 2. Distance from a point to a line. If C is a point and L is a line through A and B, then there is exactly one point P and L such that CP bar is perpendicular to AB bar. For further formula, you may see on the screen. Moreover, if Q is any point on L, then CQ is greater than equal to CP and hence P is the point on L closer to C. The shortest distance CP is given by as shown on the screen. Hence the proof of this theorem is as shown on the screen. The inequality CQ greater than equal to CP, where Q is any point on L, is a consequence of Pythagoras' theorem. Finally, as CP vectors and PA vectors are perpendicular, Pythagoras' theorem gives CP square as shown on the screen. Students, let me define the cross product of two vectors. Let x equal to a1i plus b1j plus c1k and y equal to a2i plus b2j plus c2k. Then x multiple y, the cross product of x and y is defined by as shown on the screen. The vector cross product has the following properties which follow from properties of 2 by 2 and 3 by 3 determinants. What planes are? Let me tell you about it. A plane is a set of points P satisfying an equation of the form P equal to P0 plus Sx plus Ty. Here S or T belongs to real number set where x and y are non-zero or non-parallel vectors. Theorem 1. Let A, B, C be three non-collinear points, then there is one and only one plane through these points, namely the plane given by the equation. Further, you can see on screen. Proof. First note that the above equation is indeed the equation of a plane through A, B and C, as AB and AC are non-zero and non-parallel and S, T equal to 0, 0 or 1 and 0 and 0 and 1 give P equal to A, B and C respectively. Call this plan P. See on screen. Now in the end, let us summarize what we have learned in this lecture. A vector algebra approach to three-dimensional geometry is to present standard properties of lines and planes with minimum use of complicated three-dimensional diagrams such as those involving similar triangles. Three-dimensional space is a set 3 to the power of e of order triples x, y, z, where x, y, z are real numbers. The triple is called a point. Vectors having unit length are called unit vectors. A line in E3 is a set LP0x consisting of all points P. A plane is a set of points P satisfying an equation of the form P. Two non-intersecting lines are called skew if they have non-parallel direction vectors. The inequality CQ is greater than or equal to CP, where Q is any point on L, is a consequence of Pythagoras' theorem. Vectors having unit length are called unit vectors. Vectors are unit vectors. Every vector is a linear combination of I, J and K. It is then easy to prove that two planes with non-parallel normal vectors must intersect in a line. Non-zero vectors are parallel or proportional if the angle between x and y equals 0 or pi. This is called non-zero vectors.